In insulated piston cylinder device, there is saturated liquid water at a constant pressure of 150 kilopascal. Electric resistance heater inside is turned on and 1700 kilojoule of energy is transferred. Determine the entropy change of the water during this process. Okay, so they are telling us we have a closed system, which is a piston cylinder device. The volume can change. In fact, it was a liquid water and it becomes, at least we know that some of it becomes steam because the problem statement tells us. So because the energy is transferred in, so there should be some expansion or boundary work getting out. And in a closed system, we also know that mass stays the same during the process. Now, if a question asks for the entropy change of the water, in other words, the entropy change of our system, one way we can solve it is looking at this equation. So entropy, just like other properties of a system, like internal energy or specific volume, can be found from the tables, and it will change from one state to another depending on the energy interactions. So it is just like other properties. It's a property of the system. So specific entropy, we show it with the lowercase s. So specific entropy changes in my system within the boundaries because of the energy interactions. And I can find these from the tables, and maybe I can use this equation to calculate the entropy change of my system. Usually this equation helps if the problem statement gives you enough information about if it's possible to look at the tables, because remember, at least two properties should be given for us to be able to look at the tables. One property is not enough. So let's take a look at what is given and let's sketch our system. And let's see if we can use that equation to figure out the entropy change. So here is a piston cylinder device and an electric resistance heater inside. And the amount is given. So if they give you energy interactions, its magnitude, it's probably will be needed in the energy balance. So keep that in mind. So we need to get some hints from the problem statement, just like that. And initial state properties, they give us the pressure. And they also tell us it's a saturated liquid. And of course, we know our system is water. So this too is enough for us to be able to look at the tables and read what is the specific entropy from the tables. We can also read other set of properties too, because at that pressure we know we need to look at the saturated liquid properties. Okay, and if you need other properties too, you need to read them. You can read them too from the saturated liquid water properties. So at that pressure you should look at table A5, or if you have different tables, it is at that pressure you read saturated liquid properties. So we can do that. In fact, let's write down what we can read from that table for the state 1. Okay. All right, let's read what is specific entropy at that pressure. We will need other properties too, even if you can not understand that at this point. You will figure it out later on and I will explain, but we will be needing enthalpy too. Probably for the energy balance. And then we will need the specific volume too. Let's write it like this, similar way. If you're still having trouble reading the right tables, please listen to my recordings for chapter 3 and chapter 4. It will help you to figure out how to read the right tables when the set of properties are given to you. Okay, so we are able to figure out the properties of our system at that pressure if it's saturated liquid at state 1. These are the properties. Now, how this will help us? First of all, if we take a look at it, there is some important information here. They tell us the initial volume is actually 5 liters. So if they are giving you volume, and if you can figure out the specific volume, that will tell you the mass of the water inside. And we also know that mass is not going to change in the second state too, because it's a closed system. And for a closed system, mass is the same. So what we can do is we can actually find, using specific volume, what is the mass? Because instead of mass, they are actually giving you volume. So of course, remember to use meter cube in that case. And specific volume we looked at from the tables. Actually, correct volume is this, and I'm sorry, I made a mistake there. Okay, here. And this should give you the correct units. 4.75 kilogram should be the answer. Now, this is what we were able to calculate. The next thing is, since we figured this out and this, our goal is now to find a specific entropy at second state so we can calculate entropy change of the system. Okay, so what properties do we know? What we know is it says it's a constant pressure process. That means at the second state, it is the same pressure. But thinking about it, we don't know other specific properties that can help us to look at the right tables. That's the only thing we know. And they also giving some hints that there is some steam there. But those are not enough to read the right tables. And therefore, we need another property at the second state, another specific property at the second state to be able to look at the right tables. And that is probably going to come from energy balance. I can get the hints from the problem statement because they give me energy interactions going on. So let's take a look at how we write energy balance for a closed system, or for any system, in fact. It's the same. We always start the same, right? Energy in minus energy out is equal to the change in the internal energy of our system. When we look at it, the energies that are getting in, electric, energy that is getting out in a piston cylinder device here due to expansion, the boundary work, because we know it was liquid, then became some of it is steam. So this is in there is also additional hint there. which they told us in the problem statement, this is a constant pressure process. And when it's a constant pressure process, this term comes to the other side. I don't want to show that, but what is going to happen is that this is delta U plus, we have previously shown that this can be represented as entropy change. What does that mean is, if I know this volume and I can maybe figure out H2, right? And if I can figure out H2, I also know the pressure at the second state, I will be able to read the right tables. So let's calculate H2 and then let's look at the tables to read specific entropy at the second state. I need to, okay, new page. So electric work is equal to mass times H2 minus H1, in other words delta H. And we know electric energy, we know the mass, we are trying to figure out H2, and we know H1. Okay, so what does that mean is, now we can solve it for H2, and it is going to be 825 kilojoule per kilogram. Very good. Now we know the H2, and then we know the pressure. We are also given the pressure at the second state, which was the same as the initial, which was 150. So by knowing specific enthalpy and pressure, we can able to find out what is S2, specific entropy at the second state. Good. That is our goal now. Now, just want to remind you before we move forward is that always remember, the reason we can combine internal energy with boundary work is because this is a constant pressure process. Otherwise, you cannot actually do that. So please don't assume that this is something you can apply to every situation and then every energy balance is equal to enthalpy change. No, this happens because we proved that before in our class, that in a constant pressure process, internal energy plus boundary work becomes enthalpy change. Okay, so just reminding you guys. Now, to be able to look at the right tables and read the specific entropy, we first need to figure out which tables to look at. When we look at 150 kilopascal water tables, that enthalpy, specific enthalpy they are giving us, is actually in between HF and HG. So it turns out that we actually have mixture. Okay, and what happens if we have a mixture? If I want to figure out what is specific entropy at the second state, I need to be able to use quality in order to calculate the specific entropy at the second state. But I don't know the quality. Quality can only be calculated from a known specific property, and only specific property I know in second state is entropy, right? I can use that to calculate the quality. Looking at the right tables at 150 kilopascal, we plug in HF and HFG because H2 is already known. We have calculated that from the energy balance. and HF we read that, and then okay, so the answer to quality is 0.161. Okay, no units, remember. Now we know the quality. We read SF and SFG from the same pressure, 150 kilopascal, and then find S2 now. Let's do it together. I skipped the units, but don't forget to include the units. It will prevent you from making mistakes, because you should always make sure the units that you are finding matches each term. So that is the specific entropy at the second state, and the last step is in this problem is to find the entropy change of our system from this relation, right? Let's plug in the numbers we have found so far. This is the mass, the S2 is this, and S1 is this. And therefore entropy change should be this, 4.43. Very good. Okay, refrigerant enters the coils of the evaporator of a refrigeration system as a saturated liquid vapor mixture at a pressure of 140 kilopascal. The refrigerant absorbs heat from the cooled space, which is maintained at -10 degrees Celsius, and leaves as saturated vapor at the same pressure. Okay, determine the entropy change of the refrigerant, entropy change of the cooled space, and the total entropy change for this process. Now, if a question is verbalized like this, they're asking for the entropy changes of individual component. There are ways to do it, okay? First of all, they are asking for the entropy change of the refrigerant. Just like the previous example, we might be able to use, in this case our system is a refrigerant, this. Well, this relation will only work if you are given enough information to find entropy at the first and second state. If we take a look at it, we know that at first state it's a mixture and it has a pressure of 140 kilopascal. And the second thing is we know the cooled space temperature -10, and we also know the exit property of saturated vapor at 140 kilopascal. This seems like not enough information is there for us to be able to look at the tables to read S1. We might be able to do it for S2 because it leaves as a saturated vapor at 140 kilopascal. So you would be able to find S2, which is equal to Sg. However, you won't be able to find S1. And for mass, how can we find it? There is no volume given, and it is not possible, okay? So in that case, let's sketch the system and let's see how we can solve this. So there is an open system, evaporator, right? Refrigerant gets in as mixture, 140 kilopascal, it absorbs heat from the cooled space. Okay, and the surrounding is the cooled space, right? Let's do it like this. And getting up, which is at minus 10 degrees Celsius, and leaves a saturated vapor at 140 kilopascal. Now we have seen that then it looks like I cannot use this relation to solve this problem. Now, there is also another thing we remember. We might be able to calculate entropy change of a system if it's an isothermal reversible process, which is, we can use this. For isothermal reversible processes, we have shown this from the definition of entropy. Let's see if this applies here. First of all, this is a phase transformation. It is happening at 140 kilopascal. If the mixture becomes saturated vapor, it has to be happening at this constant temperature, because phase transformation at a constant pressure has to be happening at a constant temperature for the evaporator, not for the surrounding. And then we can find it out, right? And what temperature that is from the tables. And we can figure out the system's entropy change using this relation. And this can also be applied to the surrounding, in that case the cooled space. And especially when they are giving you the amount of heat interaction, that's kind of a hint that this equation is possible to use. Now, first of all, let's remember certain things. Like within our universe, which is accepted as an isolated systems, if we want to find the total entropy change of the overall process, we need to sum up all the entropy changes of each subsystem to find the total. In this case, the subsystems are our refrigerant and also the entropy change of the cooled space, which is surrounding that. Therefore, if we want to find a total, we need to sum up all those entropy changes of individual systems, which is the refrigerant and the cooled space actually. And therefore we can use this relation. It looks like from what is given to us, it looks like we can use it, especially when this is an isothermal situation we just talked about, and reversible. Why it is reversible? Because if we remove the same amount of heat, we will still be at the same pressure, at the same temperature. Because when there is a phase transformation, you're at this is happening at a constant pressure and a constant temperature process. And reversible meant that if I reverse the process, can I get back to my original state? Yes, even if you reverse this process, remove 180 kilojoule of heat from the system, you will still be able to go back to your original state, which was 140 kilopascal and its same saturation temperature. So therefore this is reversible and isothermal because it's a phase transformation. We can assume it that way. Now therefore let's use this relation. First of all, let's find what is the temperature of the refrigerant. Because it's a phase change, it has to be the saturation temperature at that pressure, right? The pressure was 100. We look at the refrigerant tables to find that. In kelvins, remember that we always use Kelvin scale in the entropy equations. This is the temperature where the phase change is happening. Now, if I want to find the change in the entropy of the refrigerant, if we call it our system, you can also give it a different name so that you don't get confused. So entropy change of the refrigerant in this case is Q over T. This amount of heat is getting in. That's why the entropy change is positive, because remember that if entropy gets in, it carries, if heat gets into a system, it carries entropy with it. So heat is getting into your system, you expect your system's entropy to increase. In this case, our system is refrigerant. Heat getting into it, heat carries entropy with it, randomness with it. Therefore, the entropy change is positive. It increases the entropy inside. So this should be expected to be a positive volume. What about the surrounding? In this case, they called it the cooled space. Another subsystem within our universe. This is losing heat. And its temperature is always kept at the same temperature, minus 10 degrees Celsius, which makes it reversible, okay? Because even if the heat gets back to the heat, 150, 80 kilojoule heat gets back to your freezer, it's still isothermal, it's still reversible, temperature stayed the same. Therefore, minus 10 degrees Celsius is converted to Kelvin 2. It is normal that this is a negative volume, and it has to be. Therefore, especially using this direction of the heat flow is very important when you're calculating entropy change, because your freezer, the surrounding space, is losing heat energy, and therefore entropy should be expected to decrease, and you should expect a negative volume. In the individual subsystems within the universe, some entropy changes can be negative, as we observe here. But in total change has to be always positive. So find the total change because of the increase of entropy principle, that within an isolated system, in this case our universe, entropy change always has to be positive. And in fact, we have shown that before, it is equal to the entropy generated, because each time we do a process, in addition to entropy getting in and out by the heat, we also generate entropy due to, for example, friction. So therefore, entropy change in total should always be positive. And if you are not calculating a positive volume for the total change or the entropy generated, you had done something wrong. So this is the answer for the part C. Okay. All right. It needs to be perfect. Okay, this is for individual subsystems. A, B, and part C. All right. There is a rigid tank with a volume of 0.02 meter cubed. In a rigid tank, we know that the volume doesn't change throughout the process. It is filled with superheated vapor of water at 200 kilopascal and temperature. Always sketching and write what is given and what is that they're asking for. It's gonna prevent you making mistakes. After a while, the temperature drops to 40 degrees Celsius as a result of heat transfer to the room air. It's very important you identify the direction of heat flow from the question very carefully and correctly. Now determine the entropy change of the steam during this process. Okay, again they're asking within the boundaries, our system is water, they're asking for its entropy change. And if enough information is given, I should be able to calculate it in a similar way like this. Alright, seems like I have enough information because I know pressure and temperature at first state. That will help me to look at the right tables to read specific entropy at the first state. I know temperature, and I also know that specific volume is constant, because for a rigid tank, mass is for a closed system, mass stays the same and volume stays the same. If mass and the volume, they are the same, then specific volume has to be same, right? I know specific volume, I know temperature at the second state, I can find second state specific entropy. Mass can be found from the volume if we know the specific volume, and we can. Now all you have to do is look at the right tables here. This problem is not very complicated in that sense. In the first state, it is 200 kilopascal and 150 degrees Celsius. When you look at the tables, you will see this is a superheated water vapor. Now you look at the superheated tables to read a specific entropy. You can also read the specific volume. What about the second state? Second state, we know the temperature, we know the specific volume because we explained why. It is the same. Therefore, when you look at 40 degrees Celsius, what is this? Where do we locate this specific volume? And it is in between Vf and Vg. Therefore, you have a mixture. Okay, when you have a mixture, in order to calculate the specific entropy, you need quality. And only known property to calculate quality in this case is specific volume. So we're gonna read those numbers from the tables and calculate it. Okay. Make sure you can actually read these values from the tables. And the quality is 0.04914. Now we know the quality. Let's calculate S2 from SF plus X2 SFG. Never do memorization in a thermodynamics course because you won't be able to be successful. You really truly need to understand why we are doing certain things. And when you read a problem statement, the how to solve that problem should come to your mind. At least you should have options how you can use certain equations to find what is they're asking for. And therefore it requires you to be able to really grasp the concept individual device. Why do we use individual devices, and what's the purpose of these devices, and how things work is important. So we found entropy, specific entropy at the second state. And now next thing is, we just calculated, but let's create a new page here. Okay, let's find the mass. Volume is given to us in meter cubes, and we know the specific volume. I'm sorry. And the mass is this. Now, in order to find the entropy change of a pure substance, our system, we need to multiply this mass with specific entropy changes. Very good. It's negative because heat is getting out of your system. Therefore, your system's entropy change should be negative, which is expected because heat carries entropy with it, randomness with it, remember? And it should drop the entropy of your system, and the change should be negative. During the isothermal heat addition process of a Carnot cycle, 900 kilojoule of heat is added to the working fluid from a source at 400 degrees Celsius. So we have a source, and it is transferring heat to the working fluid, and the amount of heat is 900. Oh, good. 900 kilojoule. And determine the entropy change of working fluid, entropy change of the source, and the total entropy change. Again, same type of wording. Individual systems, one is our working fluid, one is our source. Subsystems within the universe, we need to sum up their entropy changes to find the total change. Now, this is an isothermal reversible process because the temperature of the because the statement says it's an isothermal process, first of all, and the temperature doesn't change, right? Especially for the source we are talking about. And we should be able to use the Q over T equation to be able to solve individual changes in the entropy. So for the working fluid, entropy change, your working fluid can be a refrigerant or water, and which is its temperature kept the same because of the isothermal process, the problem statement tells us. But the working fluid is getting the heat, so it is positive. The entropy change should be positive. Are we given the temperature of the working fluid? I guess by saying isothermal process, here they meant that. So here you need to know about the Carnot cycle. So in isothermal heat addition of the Carnot cycle, the working fluid also has the same temperature. That is what it making it reversible, because it's a Carnot cycle, and this has to happen, the theoretical assumption, at the same temperature for it to be reversible process. Okay, take a look at your notes for each stages of a Carnot cycle, which makes it reversible in theory. So here we have the same temperature. So actually we know what is going to happen at this assumed Carnot device, because entropy change in a Carnot device, entropy generated especially, the same thing, but we're going to show it that it has to be 0, because that's a theoretical device, and that's the reason this is done at an isothermal process, where they keep the temperatures the same between the source and the working fluid, because we are now able to show you with calculations that when that is the case, entropy generation is actually 0. You will see that this is happening. So one is losing heat, one is gaining the heat. So we show those with positive and negative signs. And the temperatures are the same because it's an isothermal process, which allows this Carnot device to have no entropy generation. Because remember, within the universe, total change is equal to sum up of the changes of the subsystems, right? And this should be equal to entropy generated. In this case, when we do that, it should give us 0, because entropy generation in a Carnot device is actually 0, because it's completely reversible again in theory. Okay, these are theoretical devices. That's it. A heat pump receives heat from a lake that has a temperature of 353 and supplies it into a boiler. Okay, so in between a source and the sink, our heat pump works, right? How does it work? Of course, it requires a work input to be able to take it from a sink that is at 353 Kelvin lake, and then it's dumping it back to a boiler in this case. What is the temperature of that boiler? We don't know. Okay, so now what does it say in the problem statement is the power input required is 2.5 megawatts to achieve this. That means take the heat and dump it to the boiler. Okay, we clearly identified the heat interactions too. Now what they say also, the boiler is, there's an input to the boiler, a water that is saturated liquid. Water is coming at 350 kilopascal. All right, so the boiler, it is entering at saturated liquid water. It is also exiting the boiler after getting the heat from the lake as at same pressure. That's what the problem statement says. And then at as saturated vapor. So remember, boiler is an open system. Water flows through it, and in this case that boiler acting as a source, but where the source is where we are heating, where we are dumping the heat to, because that's the purpose of the heat pump. Okay, so the heat pump here is a COP of the heat pump, Carnot heat pump, 60% of the Carnot heat pump COP. what is the mass flow rate of the water? So if we can actually identify what is going on here, we would be able to solve this problem. Because, well, we know that in a perfect ideal case, the perfect coefficient of performance for a heat pump is the reversible or Carnot heat pump. So within the heat pump, every device works perfectly. That is gonna give us the perfect coefficient of performance. But this, in real life, it is the 60% of that COP. That is what the problem statement says. So what we can do is we can start with finding the Carnot heat pump efficiency, which is the COP, of course, and then take the 60% of it, which is gonna give us the actual COP of the heat pump that we observe here. So we can start with that. So let's find the COP of the heat pump Carnot, which is reversible. We can find it from the temperatures of the reservoirs. I'm sorry, it is actually, I didn't remember it. It was, I think, 1/1 minus TL over TH for the heat pump, okay? So in this case, 1/1 minus TL is 353, TH. TH is the temperature of the boiler. It is not given to us, but you see that there's a phase change going on from a saturated liquid to saturated vapor because of the heat absorbed from the heat pump. The water in the boiler is evaporating from a saturated liquid to a saturated vapor at the same pressure. What does that mean is within the boiler there is a phase change going on, right? And because of the heat absorbed from the heat pump, the phase change is going on. And this can only happen at the saturation temperature, at that pressure. So if you look at the saturation temperature at that pressure, which is from the tables for water, it is 138.86. Okay, in kelvins it is 411.86 Kelvin. Okay, and then we can plug that in here. So the trick here is to be able to identify that temperature. And if you can do it, you can find the perfect coefficient of performance, which is 7. Remember, this is when we have a reversible perfect device, a theoretical coefficient of performance that we can find from using the temperatures of the reservoirs that the studies have shown us. Now, the actual COP will never be bigger than this, will always be lower than this. And in fact, in this problem, they are telling us it is the 60% of this volume. So actual COP of your heat pump is actually 4.2. Well, what can you find from this? Now you know the equation of heat pump COP, which is QH over power in. Now given the power is given to us, which is 2.5 megawatts, this will help us to calculate QH. Why that is important? Because it's going to help us to write the energy balance for the boiler, because we know the heat that is getting in to achieve that property changes from inlet to exit. So we find that, in kilowatts, 10,500 kilowatts. Now you know that heat is getting in, right? Which is causing a change from one state to another. It's like basically a phase change going on due to that absorbed heat. And if we want to write energy balance on the boiler, which is an open steady flow device, mass is getting in, heat is getting in, and mass is getting out. Now, how do we write energy balance for a steady flow device? We write it as the rate of energy flow getting in is equal to the rate of energy flow getting out. Energy is getting in with mass, and a single stream mass flow rate is also the same, and the heat is getting in and the mass is getting out. And then from here we can figure things out. Now they're asking for the mass flow rate, okay? So if I can solve it in a way to find the mass flow rate, so QH over H2 minus H1 is mass flow rate. Of course, here heat transfer rate to the boiler is given, or I mean we calculated it, but the entropies at the inlet and exit is something you need to look at the tables, because at the entrance of the boiler it is a saturated liquid water at 350 kilopascal, and you need to look at the tables for water and read H1, which is equal to HF. For the exit, it's a saturated vapor at the same pressure when I say H2, it's the exit, right? Exit enthalpy. And then plug it into our equation. Kilowatts is kilojoule per second, and kilojoules cancel. We end up with a unit of kilogram per second. All right, that's it. Okay, there's a rigid tank with a refrigerant in it. Initially, its pressure is 200 kilopascal and 40% quality, meaning it was a mixture. And the heat is transferred from a source that was at 35 degrees Celsius, and it causes pressure to change to 400 kilopascal. Determine the entropy change of the refrigerant, entropy change of the heat source, and the total entropy change during this process. All right, so first of all, yes, there's a phase change here, but it's not happening at the same pressure, so it might be causing our temperature to change. So for the system within the system, meaning the refrigerant, might not be an isothermal reversible process here, because pressure changes can change the temperature too. Now, if that is the case, can I find the refrigerant's entropy change from this relation? Let's take a look at it. Mass can be found because this is a rigid tank and the volume is given to me. So if I can know the specific volume, I can find the mass. And initially it is 200 kilopascal and 30% quality. Wow, they give us pressure and quality. That is enough for me to calculate the rest of the properties. Therefore, for S1, I can for sure figure out what is the specific entropy. In fact, I can find other properties too. Now, at the second state, what do we know? We know pressure drops to 400. We also know the same volume because it's a rigid tank. Seems like I have enough information, two properties, enough for me to look at the tables to read specific entropies for my pure substance, which is refrigerant in our system within the boundaries. Therefore, entropy change of it can be calculated from the specific entropy change times mass. I can use this relation. So let's do that, okay? Pressure is given to us as 200 kilopascal and the quality is given to us as 0.4. Together, this will help us to calculate the rest of the properties. I'm not gonna solve and write all of it. I'm just gonna write down the formula and you guys can look at the tables to figure these out, because at that pressure you can read UF and UFG for refrigerant, and the answer should be this. Same, you find S1 using quality. So we can find the specific volume too, same way. I always do the same mistake for some reason. Okay, and very good. And same way we look at the second state, we know the pressure at the second state, and then we know specific volume. It turns out we have also a mixture. And we again find the quality first using specific volumes at that pressure, this time 400 kilopascal. You read these from the tables and the answer is this. Now we can calculate U2 from UF plus X2 UFG. And same way you calculate okay. Now S2 and S1 specific entropies at first and second state is known. All we need to do is find the mass. Since they give you the volume, you can divide it to the specific volume, and this will help you to calculate the mass, which is 12.37 kilogram. Okay, so we know everything that is necessary for us to calculate our pure substance, the entropy change, which is mass times specific entropy change. And which is okay. So this is our systems. In other words, our system here is a refrigerant. It's a positive change. It gets the heat. That's why it is normal. It's a positive change. The entropy change increased. I mean, the entropy increased, and it creates a positive change. But now we don't also, this is not enough. We also need to find the sources entropy change, and the source is isothermal. Remember, source doesn't change its temperature with energy interaction, so it is always at the same state whatever happens, and therefore it's an isothermal reversible process for the source. And we can use, to calculate the source entropy change, we can use Q over T. But we are not given the Q. We don't know what is the heat interaction. But actually we can find it from the energy balance, because we know how properties changed from first to second state. This would help us to be able to calculate what amount of heat needs to get into the system to achieve that property change. Here you need to remember to write energy balance for a closed system. Energy in minus energy out is equal to the change in the internal energy of our system, right? And energy getting in is Q. There is no energy getting out, causing a change in the energy of our system. And we found the mass. We know the internal energies. We calculated using quality at first and second state. All right, now that is the heat interaction, and we can use that to calculate the source entropy change, because while studying sources, we know these are isothermal systems. So what is going to happen is Q over T, but the source is losing heat. So in order for us to represent the direction of the heat flow, because the source is losing heat means its entropy should be decreasing, we need to use a negative sign to represent that. The temperature of the source was, I think, 35, okay, 35 plus 273, 388 Kelvin, and minus 3.434. This has to be a negative value. If it's not, you're making a mistake. Now we know the sources entropy change, we know the system's entropy change, and we can sum those up, sum those subsystems to find the total entropy change within the universe is the system and source was minus 3.434, and the source was let's remember if it's correct. Okay, correct. And then next is, this has to be always positive, right? The total has to be positive always, because always entropy is being generated. Alright, so there is a rigid tank with water in it, 5 kilograms saturated vapor at 100 degrees Celsius. The steam is now cool to ambient temperature of 25. Sketch the process with respect to saturation lines on TV diagram. What is the entropy change of your system? And what is the total entropy change of this process? All right, very good. What are they giving it to us is, first of all, in first state, we are given the temperature, and quality is 1 because it means it's a saturated vapor. This will give me a lot of properties that I need to find, and I can do that. Let's start with state 1. Temperature is 100. It's a saturated vapor of water, and we look at the tables to read. For the first state, specific volume is the Vg. Specific entropy is the Sg at the first state. And we can also find other properties if we need to. Now for the second state, what we know is temperature because they tell us so. Another thing they didn't directly tell us, but what we know is the specific volume is the same since it's a rigid tank. So this will tell you, I'm not sure, I think it's a mixture. This will tell you it's a mixture, and then if that is a mixture, you need to find quality first from specific volume, which should lead you to and then using quality you figure out at that temperature what is U2, again this is not happening at the same temperature, it's not isothermal situation. The pressure the temperature is changing, so we need to use mass times specific entropy change to be able to calculate the total entropy change in this process. Okay, so when we look at the TV diagram, and if this is our dome, right? Initially we had a saturated vapor which should be somewhere here, we don't know. At a constant volume the temperature is dropping, right? It was 100 and it dropped to 25 at a constant volume. Okay, so we had saturated vapor. Now at second state we have mixture. So this is the TV diagram, and we can now able to calculate what is the entropy change for our water, in other words our system, because all we have to do is, you can name it, label it system or water, as any way you feel. You're not gonna mix it with other calculations. You can use any subscript that is convenient for you. And the mass is 5. S2 is, we found it. S1 is also, we found it from the tables. I hope I have enough space here. Let me carry this to here. And so of course that this is negative because your system is losing heat. And now we found that, let's take a look at actually how we can find the rest. And the rest is the, first of all, they're asking for the entropy change of the steam. We found that it's negative because heat is getting out and heat carries entropy with it. And the next thing is find the total. So for me to be find the total entropy change, in other words, they could have also asked for entropy generated during this process, because remember, within the universe, the total change is equal to entropy generation and is always positive. In order for us to find that, we need to sum up of subsystems entropy change. We have water and we also have surroundings. So we found the water's entropy change because we know how a pure substance entropy change can be found by looking at the tables. But when it comes to the surrounding, let's take a look at it. So here the surrounding, okay, so can we assume this is isothermal situation? Why is that? First of all, the temperature drops to 25. It becomes in equilibrium with the surrounding temperature, which is also 25. And also you can think about the surrounding area as the sink at this point. Okay, so because only way to calculate this surrounding entropy change is actually using this relation. We don't have any other form of calculating this, and we need to know Q and then the temperature, which is 25. We know that to be able to calculate this. But now we notice that we actually don't know the heat interaction. Again, the heat interaction will come from energy balance. So now we need to write energy balance here. Again, for a closed system, energy getting in minus energy getting out is the change in the internal energy of our system. Here it's a rigid tank. There is no energy getting in. It is only getting out. So heat that is getting out is causing a change in the internal energy of your system. So if we plug the numbers in, right, getting rid of that negative sign, if we plug the numbers in from the tables, we found U1 and U2. It is 11,562 kilojoule. That is the heat getting out of our system, which is getting in to the surrounding. So therefore, if we want to find the entropy generated, or if we want to find the total entropy change, we need to sum up the entropy change of our water and plus the surrounding. So for the water, we calculate it to be a negative change because we know that entropy is getting out with the heat, and plus Q over, I made a mistake in the units. Now I understand it because now I'm writing 298 Kelvin because it's 25. This has to be Kelvin too. So here the positive, always the change is positive in total, which is 5.44 kilojoule per Kelvin. Okay.